So hello my dears. So today I am going to discuss about very important session in electronics, that is nothing but mass action law. Okay, this is associated with the intrinsic and extrinsic semiconductor. Any semiconductor you can consider this is associated with the semiconductor. Okay, because semiconductor only there will be the conduction due to electron as well as the conduction due to holes happening. So mass action law states that in a semiconductor, intrinsic or extrinsic, the product of carrier concentration of electrons and holes at thermal equilibrium in the sense at a constant temperature. Constant temperature is equal to the intrinsic square of intrinsic concentration. Okay, in a semiconductor means it may be anything. It may be like intrinsic or extrinsic semiconductor. The product of the carrier concentration. The carrier means in an intrinsic semiconductor or in an extrinsic semiconductor, the carriers are nothing but what? The charge carriers, which are nothing but electrons as well as the hole. In the case of conductor, only electrons are responsible for the conduction, but in the case of a semiconductor, both the electrons as well as the holes are responsible for the current in a semiconductor. Okay, so carrier concentration of electrons and holes, the product of the carrier concentration of the electrons and holes at a thermal equilibrium means at a constant temperature is equal to the square of the intrinsic concentration. That means by words we can say that N into P is equal to Ni square. This is very important. This one word question also you may expect from this. What is mass action law? Okay, what is mass action law? So just note this, my dears. So N into P is equal to N into I square, where N is nothing but the electron concentration, P is nothing but the hole concentration. Okay, concentration is nothing but number per particular volume, that is called the concentration in three-dimensional view. Okay, so N into P is equal to Ni square is nothing but the mass action law. This is the definition is very important, my dear. Definition is very important. Okay, next term regarding the semiconductor is nothing but conductivity represented by sigma. Conductivity represented by sigma. So what is mean by this? There is nothing to explain more than this, my dear. Just product of the electrons into product of the whole concentration will be equal to Ni square. Intrinsic concentration is nothing but without or before doping. Before doping, what is the concentration? Okay, before doping, what is the intrinsic concentration itself? Electron concentration, that is you have to note. Ni means intrinsic concentration, which is nothing but the electron concentration. Okay, electron concentration, because electrons and equal number of electrons and holes will be there in intrinsic conductor. Suppose we are assuming in intrinsic semiconductor. Okay, intrinsic semiconductor are poor conductors, like no, it is like at absolute temperature very feeble conductivity is there in intrinsic semiconductor. So almost electron as well as the holes are same there. That is why they are taken like Ni square. Okay, if you have taken for here also it can be taken like N into P, but Ni square why they have taken means in extrinsic semiconductor only a large number of variation from electron the holes happen. Not large number in the sense not lakh to 1, not crore to 1, but I already told you now, 10 raised to 8. The doping is actually for 1 atom in 10 raised to 8 atoms. So that much variation will be there. But it can be negligible now. It can be also negligible. But it is like a theory, n into p is equal to ni square. Don't go much deeper into that. It is all chemistry. We don't want to go much deeper into that. Just remember this expression, my dears. Just remember this expression. That's more than enough sufficient. Next, conductivity sigma. In a conductor, conductivity sigma is nothing but, my dear, n mu q. Okay, where n is nothing but the carrier concentration, and mu is nothing but the mobility of electron, and q is nothing but a charge. I mean total charge. Total charge. My body is clear to you now? Yes. Okay. So q is nothing but total charge. So this is a general equation for the conductivity. Conductivity is nothing but n mu q. In semiconductor, my dear, in semiconductor, total conductivity sigma is equal to nothing but P mu q plus n mu q. Here n mu n and mu p. Mu n and mu p. Where mu n is nothing but the mobility of electron and mu p is nothing but the mobility of holes. N is the electron concentration and p is the hole concentration. Okay, I will tell that also. N is nothing but electron concentration and p is nothing but hole concentration, and mu p comma mu n mobility of holes and electron respectively. Mobility of holes and electron respectively. Okay, q is the total number of charge. So this is the conductivity in a semiconductor, and you have to note one important thing here. My dear. You have to note one important thing here. The conductivity is actually by the total conductivity is nothing but the conductivity due to P, that is the hole, conductivity due to the electron. Okay, so total conductivity is nothing but this is the conductivity due to electron. So electron, you can write like two parts is it, one is concentration for electron and one other is for hole. Electrons as well as holes. Okay, so what is the relationship between mobility and temperature? That is, we have mobility mu inversely proportional to 1 by t raised to m. You know that, na? Mobility is inversely proportional to 1 by t raised to m. And when temperature rises, carrier concentration also increases. That means we can say that N or P, that is the carrier concentration, directly proportional to temperature. We have these two relationships. One is nothing but, my dear, mu proportional to 1 by t raised to m, and next one is N or P directly proportional to temperature. But the change in N or P directly proportional to temperature is much higher than mu inversely proportional to 1 by t raised to m. That means This is much higher than this. That means for same change in temperature, same change in temperature, for a semiconductor, my dear, for a semiconductor, for same change in temperature, for a same change in temperature, this N or P, that means the change in concentration of electrons or the change in concentration of holes with respect to temperature is much higher than the change in mobility with respect to the temperature. Okay, is it clear? When we increasing the temperature, this should be lower. We know that, no? We know that when we are increasing the temperature, this should be lower. Mobility will be lower, means the ability to move will be what decreases, or the collision will be more and more there, so that the conductivity will be reduced. But at the same time, when we are increasing the temperature here, the N will be increased there. So this decrease is lower than this increase. That means this increase is much higher than this decrease. In fact, I mean all over, whenever we are increasing the temperature, the carrier concentration increases much faster than the decrease in the mobility of the carriers. So that in short, or in effect, when we are increasing the temperature, the result is nothing but, my dear, increasing the concentration of carriers, increasing the concentration of the carrier. So the result is increasing temperature results in increase in carrier concentration, or increasing conductivity. That's all. Or I can say that conductivity sigma directly proportional temperature for what, my dear? For semiconductor. This is for semiconductor. That is why when we are increasing the temperature of a semiconductor, what happens? Its conductivity increases. Its conductivity increases. That is the semiconductor exists what, my dear? Positive temperature or negative temperature? Negative temperature coefficient of resistivity. That means whenever we are increasing the temperature, its resistivity will decreases. Or it can be same thing. You can also write like the resistivity rho inversely proportional to 1 by tau. Rho inversely proportional to 1 by tau. Whenever we are increasing, that is conductivity increasing, means conductivity is nothing but, my dear, reciprocal of what? Resistivity. So these two important things you can obtain from a semiconductor. You know this, but this is the reason. We already know this now, but this is the reason. Now we exactly found out what is happening inside the semiconductor when we are increasing the temperature. That means the change in concentration is much larger than the decrease in the resistivity. I mean decrease in the mobility. Mobility decreases, we know that, I accept, but with respect to the change in carrier concentration, this is multiplies like a bomb. This is multiplied like an explosive manner. But this mobility decrease is not like an explosive manner. That is why we get more and more carrier, we get more and more electrons or hole for the conduction, so that the total conductivity of the semiconductor will be increased. This is for semiconductor. This is for semiconductor. Is it clear? So what happened for conductor, my dear? What happened for conductor? What happened for conductor? So this is for semiconductor, na? I know what happened for conductor. So in conductor, my dear, in conductor, what happened? N mu q is the equation, right? N mu q is the equation. Okay. So in conductor, when T increases, we can say that T increases, there is already there is already large number of carriers for conduction. So a change in temperature doesn't affect much in terms of concentration of carriers, but it affects badly on mobility. That is sigma inversely proportional to what? 1 by mu. Am I right, my dear? Sorry, sigma proportional to mu. Sigma proportional to mu, which is inversely proportional to 1 by T raised to m. Which is inversely proportional to what? 1 by T raised to m. So whenever we are increasing the temperature, it's badly affect the mobility. The return things are nothing but, my dear, in a conductor there is already enormous amount of charge carries in a conductor. So even if we are increasing the temperature, suppose you assume there are 1 crores of electrons. So say you increase the temperature by 1 or 2 degree or 10 degree even, you will get 1 crore 10,000 electrons. The change is it noticeable? No. There is already huge amount of electrons are there for conduction. Even if you are increasing the temperature by 10 or 20 degree now, there will not be that much significant in the increase in the carrier concentration. But there will be significant in what, my dears? There will be significant in the mobility, because mobility is inversely proportional to the temperature. We already know that. There, why it didn't that much what observable means, more than that there will be increase in the carrier concentration. That is why it's not that much observable there. But in the case of this conductivity here, in the case of conductor, what happened? There is already enormous amount of electrons. So even if you are increasing the temperature, the concentration increase of the electrons or charge carried is not that much evident or not that much visible. But the visible thing is other side. What is the other side? The visible thing is nothing but the decrease in the mobility. So when we are increasing the temperature, this term is, if you increase in this term will be decreased. This mobility term will be decreased. Mobility is nothing but, my dear, ability to conduct, in other words. Now, mobility is nothing but what? Drift velocity. Its ability to carry current is called the mobility. Whenever there is a super mobility, then only the conduction will be that much super. If the mobility is hindered by something, if the mobility is objectionable by something, then what happened? There will not be that much conduction. So here what happened, my dear, when you are increasing the temperature, the mobility will be decreases. Mobility is directly proportional to conductivity, so conductivity decreases. So in a conductor we can say that, resistivity directly proportional to temperature. Resistivity directly proportional to what? Temperature. But in the case of semiconductor, what? Resistivity is inversely proportional to temperature. These two important things we have to note. In a conductor, when we are increasing the temperature, its conductivity will become higher. In a conductor, that is the conductor and semiconductor opposite. That's all. Semiconductor, whenever we increase the temperature, conductivity will be higher. In the case of a semiconductor, when we are increasing the temperature, its conductivity will become lower. In the case of a conductor, opposite in the case of a what? Insulator. Is it clear? The same thing actually happened in the insulators also, because the ideal insulator is nothing but vacuum. Even in large temperature, the vacuum also conduct. So nothing in the universe is likely to be, say, an ideal insulator. Okay, the ideal insulator is not exist in the universe. Even our vacuum will conduct, because if you have one atom in the whole vacuum, that atom will generate more atoms by during the collision or bombardment. Okay, high voltage DC, that is a beautiful subject, my dear. I think in the S7 you might have studied that. that explain really what is an insulator, how this collision and all happens there. That what indicate exactly. So if you study that subject, then the things will be very easy for you. Okay, so that's all about the conductivity in terms of conductor as well as the semiconductor. Okay, is it clear, my dears? Is it clear? Next, you have to see Pn junction diode. Pn junction diode. So first of all, what is the difference between So first of all, what is the difference between an atom and an ion? What is the difference between an atom and ion, my dears? Atoms are nothing but electrically neutral because it contains equal number of protons as well as electrons. But in the case of an ion, it is either less of proton or either higher of proton. So depending upon that, its charge may be either plus or minus. Suppose an atom is losing an electron, then it is called as a donor atom. If the atom is losing some electron, means there will be a deficiency of electron, and in it its charge will be positive in nature. The reverse case will be in the case of an n-type. For p-type. A p-type is formed by actually what? An acceptor atom, right? See, the acceptor atom. That means it having what, my dear? It having an excess of p. It having an excess of hole there. It having an excess hole there so that it can. Okay, don't worry, confused. No confusion. I will say one by one. A donor atom is nothing but, my dear, an atom which is capable of giving electron is called a donor atom. If it is giving electron, what happen? It having a deficiency in electron. So in its atomic structure, what happen? There will be one, it loses an electron, so there will be a deficiency of electron, so there will be one whole, what? One whole excess. that one hole excess makes the total atom like a what? Donor atom, and it make a total atom a positive charge. That's all. Is it clear now? Is it clear now? So if an atom loses an electron, there will be a deficiency in electron, no? In atomic structure. Deficiency electron means increase in one proton or increasing one hole. So increasing one proton means a positive charge. That is called a donor ion. Donor atom. If it loses what? An electron means now it is not electrically neutral. If it is donate an electron means there will be unbalance in the number of electrons as well as the protons. So now the atom is not electrically neutral. It is called a donor ion because now it is having a positive charge. So what is the difference between ion and atom means? Atom is nothing but electrically neutral thing, but this ion is nothing but charged things. Either it is having a positive charge or it is having a negative charge depending upon whether it is losing the electron or it gains the electron. That is why donor ion. So donor ions are charged, having some charge, effective net charge, but in the case of donor atom, it doesn't have any net charge. The same thing, the opposite will be for what? Acceptor atom and acceptor ion. Is it clear? Is it clear? That means acceptor atom means the atom can capability of absorbing an electron. Okay, an atom having a capability of absorbing an electron. If it absorbs an electron, my dear, there will be an excess in the negative charge. One negative charge excess there because electron having negative charge. So that making it a negative one. So acceptor atom is represented by this plus an electron. Acceptor ion is represented by simply a negative charge. Okay, so in our hand we have P material, we have N material. What happens if I diffuse it together? Excuse me. Okay, sorry. So what happened if we diffuse it together? What happened, my dear? Let's see. This is P-type material and this is N-type material. I diffuse it together means some of the acceptor atom here in the P region, some of the donor atom in the N region diffuse automatically. Diffuse automatically because they are come into contact. These two wafers are coming into contact. So what happened? They will diffuse automatically, and in short, this donor atom will donate one electrons to this acceptor atom so that this will be positive, and the acceptor atom will expect one electron so it will be negative. So there will be a layer of, or there will be a band of, or there will be a layer, simply a layer of ions. One side consists of donor ion, other side consists of acceptor ion formed, called the depletion layer. And this depletion layer consists of what, my dear? Plus minus charges. If there is plus charge and minus charge separated by a distance, form the what, my dear? There will be an electric field. There will be an electric dipole, or there will be an electric field forms. So here also an electric field forms. That electric field is represented by ED. So ED is nothing but, my dear, depletion electric field, or electric field in depletion layer. Electric field due to depletion layer. That is correct. Electric field due to depletion layer. Am I right, my dear? Electric field due to depletion layer. Is it clear? So this is nothing but the conjunction of Pn junction. So naturally there will be what? a diffusion process happens. So diffusion process happens only when the concentration of the charge carriers is high at both ends. Okay, high at the both ends. Is it clear, my dear? Is it clear? That means some of the electrons and holes in the two regions will recombine. Okay, so that's all about the depletion. Depletion layer formation. That is how the depletion layer formation. Now we will see what are the current there in the conjunction. What are the currents there in the conjunction? I will make a table so that it will be very easy for you to refer. Types of current, direction of current, and direction of flow of charge carriers. Just make a table because it is very easy then. So I will write one by one, my dear. Types of current. I will say like this: diffusion current due to holes. Next, diffusion current due to electrons. Drift current due to holes. Next, drift current due to electrons. And the diffusion current due to holes, I will say diffusion current due to holes. It's a Pn junction. So diffusion current due to holes is like this. Diffusion current due to electrons. Diffusion current due to electrons. Electrons are moving like from current will be opposite. Drift current due to holes. So in the end region there will be, I will explain. Okay, I will explain. Drift current in the end region. Drift current due to hole. So that will be like this. And drift current due to electrons. That also like this. And direction of flow of charge carriers. Direction of flow of charge carriers. Holes, electrons, and again holes, electrons. Okay, listen, my dears, listen. So this table illustrates everything regarding the Pn junction. I will explain one by one. So due to the conjunction, my dear, due to the conjunction of the P and N, if the circuit is actually before it biasing, or before it is externally connected, this word is very, very important. Before it is externally connected to the circuit, what happens I will tell you. So inside the material, my dear, in the material there will be some currents, and you may wonder that, sir, for the flow of current there should be a closed path now. Yes, here is a closed path. It is not meant to be external to the Pn junction, but it is meant to be internal to the Pn junction. That internally itself it forms a closed path. It's very interesting. Now listen. So diffusion is nothing but, my dear, diffusion, the term diffusion is nothing but, see, I can say that the perfume aroma is diffused into the air. Why? Because if there is a diffusion, means there should be a concentration gradient. That means there will be flow of matters from higher concentration to lower concentration is called the diffusion. Matters means flow of electrons now. Matters means flow of charges now. Finish. So In the case of a PN junction diode, my dear, just I will show you now. In the case of a PN junction diode, what happened here? Here P means it contains lots of holes. In N means it contains lot of electrons. So there will be a flow automatically from this hole to electron for the recombination. So there will be the flow of holes like this, and there will be a flow of electron like this as the majority carriers. So I can say that there will be the movement of holes from left to right. Left to right there will be a movement of holes. That is why I indicate like this. I will mark like this because this is the hole and this is electrons, and this is again holes, and this is again electron. Super na? So holes will be moving from here to here, and there will be a current called a diffusion current due to holes. Diffusion current due to holes, and that diffusion current is type of current is represented like IP, and because we know that P to N there will be a flow of holes, in the same direction there will be a flow of current also. So P to N there will be a flow of holes, the same direction there will be current also. That is why diffusion current due to holes. It is from here to here, left to right. At the same time, my dear, in N region contains a lot of electrons. Its majority carries are electrons. So obviously there will be a tendency of that electrons to come to this side of P region and recombine. So what happened, my dear? The electrons from this region move to this region. So electrons from moving from right to left. Electrons will be moving from electrons will be moving from right to left. Electrons will be moving from current is correct. No, current is correct. So diffusion of electron will be what, my dear? It is correct. Diffusion of electron is from here to here. So opposite direction will be the direction of current. So electrons diffusion from right to left, that is the arrow, but at the same time the current will be flowing in opposite direction of the electron. That is the conventional way, right? That current is represented by IN because it is the current due to electrons. Next, what is meant by drift, my dear? Drift are nothing but due to minority carriers. Drift are nothing but due to minority carriers. I will explain. Due to minority carriers. Here also due to minority carriers. So what is the drift now? See, drifts are nothing but, my dear, in the case of this P contains more number of majority as holes, but less number, a very small number of electrons also, because none of the material we can't make like a pure P or pure N. A small amount will be there which is not P or not N in the N and P region respectively. So in the P region there will be small amount of electrons also. Small amount of electrons also as the minority carriers. Small number of electrons also as the minority carriers. So what happened? There will be electrons. Electrons will be, see, in the N region there will be small number of holes also as the minority carrier. So the holes here in the N region, the electrons here in the P region as minority carrier also have an attract or have a property to compare each other or diffuse each other. So what happened? The electron will move from here to here. So the drift current due to electrons will be what? Drift of electrons will be from left to right. So the current will be in opposite direction. This current is represented by IN dash. Similarly, this is nothing but IP dash. So the same manner, there will be holes here as the minority carrier. So that will try to compare to the electrons in the P region as the minority carriers. So what happened? Holes will be moved from here to here. So the same direction current will be flowing. The holes will be moving from right to left. Bus. If you know this table, you can talk something. You can talk a lot about this PN junction diode. This is before biasing. I repeat the term, there is no external connection. There is no external connection. And this explains how the depletion layer forms in between this P and N. So what happened? Some of the electron will be diffused here, some of the holes will be, some of the holes will be diffused here, some of the electron will diffuse here. Then forms a depletion layer ED. There forms the depletion layer ED. That means even though there is no external connection, there is a flow of internal current. There is a flow of internal current. And when this internal flow will stop, my dear, when this internal flow will stop, that means after particular time, I can say that the total IP diffusion plus IP drift equal to 0. Similarly, total IN diffusion plus total IN drift is equal to 0. That means the total diffusion current plus Hall current, drift current will become 0. Again, total diffusion current due to electron plus drift current due to electron will be 0. If the total current is equal to 0 means across the junction there will not be any current. Am I right? Because there is nothing in external. It is everything in internal. So if the total current is 0 means there will be some barrier existing between this P and N junction. And that is nothing but, my dear, potential barrier. That means there exists a potential barrier. A potential barrier called the depletion layer. That means in the depletion layer is nothing but, my dear, the region or the band or the space in the PN junction devoid of what? Devoid of charge carriers. Charge is there because that is why there is a potential. That is why there is an electric field. There is an electric field means there are some charges. There are some charges, but there are no charge carriers. Very important to note these two words, my dear. There are charges, but there is no charge carriers. Charge carriers are nothing but either electrons or holes. There is nothing. Electrons or holes are nothing there. But there are ions, positive or negative ions. That is why this region is depleted of charge carriers, devoid of charge carriers. That is why it's called a depletion layer or barrier, potential barrier or the potential barrier. Is it clear, my dear? Is it clear? Okay, so next, diode forward biasing. Diode forward biasing. Diode forward biasing. So what happened? Listen. See, my dears, junction forward. This is the potential barrier. Potential barrier. See what happened if I connect this PN junction, already marked in a PN junction, this PN junction diode to a voltage source like this. A voltage source like that means I connect P region to positive side and N region to negative. This is called a forward biasing. So what happened at that time? If this is called PF, that is a forward voltage. There exists a potential barrier, my dear, which is nothing but Vy. There exists a potential barrier in the diode which is called Vy. If we apply a voltage Vf greater than this Vy, what happened? Depletion layer vanish. That means there will be an internal electric field due to the natural diffusion, and there exists a potential barrier, that is nothing but Ed. If we are applying an external electric field which is more powerful than the internal electric field formed by the natural diffusion of PN junction, what happened? Then where will be these holes now? They will force, because this is an external field now. This is P and holes also contain the positive charge. There will be a repulsive force from this positive to this positive charge. So the holes will push across this junction, so that this junction will start breaking. There will be penetration of, it's like a bullet now. It's like a bullet penetrating like across this junction, so that the junction will slowly vanish, and there will be again a flow of conduction, flow of electrons happen, but that flow will be throughout the external to the internal. This will be the direction of the flow of charge carriers. That is called the biasing of PN junction. That is called the biasing of PN junction. So in the biasing, what happened? There will be a flow like this, so that the conduction will happen, so that the breakdown will be happen. So it is only if the forward voltage greater than Vy. The forward voltage greater than Vy. This Vy is nothing but, my dear, knee voltage. Vy is nothing but sometime it is called a cut-in voltage also. This Vy is called a cut-in voltage. Cut-in voltage, and which is nothing but 0.7 voltage for silicon and 0.3 voltage for germanium PN junction. Okay, that also you have to note. That also you have to note. And in semiconductor, one more thing, the one thing I have to do, total current. The total diode current in a semiconductor, that is ID, is nothing but due to electrons plus ID, that constitute due to holes also. So the total diode current in a semiconductor, that is semiconductor diode, is nothing but IN plus IP, that is the current due to electron plus the current due to holes. That's all. Current due to electrons plus current due to holes. That's all. Okay, so that's all about today's session, my dear. We will continue in the next session. Okay, thank you.